In this lesson, we're going to continue our study of series and convergence. Let's start with some review. So first, what is the definition of a convergent and a divergent series? So a sum series from n equals 1 to infinity of terms an, this will converge if the sequence of partial sums S sub n converges, and diverge if the sequence of partial sums S sub n diverges. Remember that Sn is a1 plus a2 all the way up to an, as in you only add a part of the series, not all of it. So we had two examples of series where we could determine convergence and divergence. So a geometric series summed from 0 to infinity, ar to the n. This will converge if the absolute value of r is less than 1. And in that case, this actually specifically converges to a over 1 minus r. And this will diverge if the absolute value of r is bigger than 1 or equal to 1. What is the test for divergence? So given a sum from n equals 1 to infinity an, if the limit of the term, so limit as n goes to infinity of the an's, is not 0, then the sum from n equals 1 to infinity an, then nothing diverges. So give an example of a series whose terms approach 0 as n goes to infinity, but the series is divergent. So the classic example is the harmonic series. And that is the sum from n equals 1 to infinity 1 over n. So we know that as n goes to infinity, 1 over n goes to 0. But this series diverges. A thing to note, just because the terms an go to 0, this does not mean the sum of an converges. It leads you to believe that that might happen, but it does not necessarily mean that it happens. So next, verify that the following infinite series diverge. Explain your reasoning. So for this first one way to prove divergence is to use the test for divergence. So we're going to find the limit as n goes to infinity of the terms in this sequence. That's the same thing as ln of the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1. So that's natural log of 1/2. And whatever that is, it's not equal to 0. Natural log of 1 is 0, but natural log of 1/2 is not 0. And so as the terms do not approach 0, this series diverges. Poor spelling. Diverges by the test for divergence. So for this next one, we're not going to use the test for divergence, even though it probably is theoretically possible. We are going to break this into two geometric series. So make this 2 to the n over e to the n plus 4 to the n over e to the n. So that's the same thing as the sum from n equals 1 to infinity, 2 over e to the n, plus the sum from n equals 1 to infinity of 4 over e to the n. Now re-indexing, we get the sum from n equals 0 to infinity, 2 over e to the n plus 1, plus the sum from n equals 0 to infinity, 4 over e to the n plus 1. And one more step before we can draw a conclusion. Sum from n equals 0 to infinity, 2 over e to the n, plus the sum from n equals 0 to infinity, 4 over e to the n. Okay, now as e is about equal to 2.71, we know that 2 over e is less than 1, so our first series does converge. But 4 over e is going to be bigger than 1. So the second series diverges, and so the whole series diverges. Verify that the following series converge and find the sum. So our options for converging series are converging geometric series and converging telescoping series. These are probably, this one is probably geometric. So first we have 3 times 3 over 4 to the n. Now if we're going to find what this converges to, as it is a geometric series, our indexing must begin at 0 to use our formula. So we're going to have 3 times 3 over 4 to the n plus 1. So that's 3 times 3/4 times 3/4 to the n. And this is a geometric series with a equal to 9/4 and r equal to 3/4, which is less than 1. Thus it converges. Specifically, it converges to a over 1 minus r, or 9/4 over 1 minus 3/4, which is the same thing as 9 over 4 minus 3, or 9. Okay, next one. This seems kind of strange, but it actually will converge. Sum from n equals 1 to infinity of 1 over root 2 to the n. Alright, so first thing to notice is that your indexing set is going to need to start at 0 if you're going to use the geometric series formula. So sum from n equals 0 to infinity, same thing as 1 over root 2 to the n plus first. Note that 1 to the n plus first is just 1. So same thing as the sum from n equals 0 to infinity, 1 over root 2 times 1 over root 2 to the n. Now as square root 2 is approximately 1.41, 1 over root 2 is going to be less than 1. And so thus this is a convergent geometric series. it converges to a over 1 minus r, so that's 1 over root 2 over 1 minus 1 over root 2, which if we multiply by root 2 over root 2, we get 1 over root 2 minus 1. Verify that this series converges and find its sum. So whenever you see two expressions differing by a minus sign, well, think, probably something telescoping. Let's see if that's possible. So let's list a partial sum. The first number we plug in is 4. So we have 1 over root 4, or 1/2, minus 1 over root 5, plus, that's plugging in 4. Now plug in 5. 1 over root 5, minus 1 over root 6. And look, that guy cancels that guy. So that's plugging in 4, 5, plug in 6, 1 over root 6, minus 1 over root 7. Probably enough to convince you that a bunch of stuff is canceling. The last term in your partial sum would be 1 over root n, minus 1 over root n plus 1. One prior to that, 1 over root n minus 1, minus 1 over root n. And you can see that this guy and this guy are going to cancel. So the only things left after cancellation here will be 1/2 minus 1 over root n plus 1. And as n goes to infinity, Sn, the nth partial sum, approaches 1/2. So thus your series converges to 1/2. Determine whether the following series converge or diverge. If they converge, find the sum. If they diverge, explain why. So my first instinct here is to try to break this into a sum of two series. So 3 times 1/5 to the n, and the sum from n equals 1 to infinity, 2 over n. Now this first one, that one's geometric. It's not indexed right, correct? It's not indexed right to find the sum. But the r is 1/5, which is less than 1, so this will converge. But the second one, notice this is the tricky one. This is the sum from n equals 1 to infinity, 2 times 1 over n. And that's that tricky one. That is the harmonic series, or you could think about it as 2 times the sum from n equals 1 to infinity of 1 over n. So the second sum is twice the divergent harmonic series. And so thus this series diverges. All right, this next one, tell me if this series converges or diverges. And we can't use a geometric series because this is n squared, not 2 to the n. So my other thing to try is probably try the test for divergence. You don't have very many tools yet, so that would be one of the things to try. So find the limit as n goes to infinity of en over n squared. And notice that as n goes to infinity, the numerator goes to infinity, and so does the denominator. So this is an example of using L'Hopital's rule. Now I have to be a good mathematician and change my n's to x's because L'Hopital's rule only applies to functions. So there we go. That will be e to the x over 2x. Still infinity over infinity, so apply the rule again. E to the x over 2, and that will be infinite. So the things that you're adding up are going to infinity, which is definitely not 0. So as the terms go to infinity, this series diverges by the test for divergence. Now, some properties of infinite sums: if you have some convergent series, and A, B, and C are real numbers, so if your sum of your first series is A, sum of your second series is B, then you have the following properties. So the first one says that the constant can factor out of your convergent sum. The second one says that you can sum the convergent sums individually. And the last one says you can sum the difference of convergent sums individually. This is not true if the sums are divergent. So we're going to use that to sum this one. So find the sum from n equals 1 to infinity of 0.7 to the n and 0.9 to the n. So this is a sum of two convergent geometric series. So this is 7/10 to the n plus the sum from n equals 1 to infinity of 9/10 to the n. Now both of those need to be reindexed. So sum from n equals 0 to infinity, 7/10 to the n plus 1, plus the sum from n equals 0 to infinity, 9/10 to the n plus 1. And so that's the same thing as the sum from n equals 0 to infinity, 7/10 times 7/10 to the n, plus the sum from n equals 0 to infinity, 9/10 times 9/10 to the n. Okay, adding those things up, the first one will be 7/10 over 1 minus 7/10. The next one will be 9/10 over 1 minus 9/10. That's the same thing as 7 over 10 minus 7 plus 9 over 10 minus 1. So we have 7/3 plus 9. 7/3 plus 27/3 tells us that this sums up to 34/3. Now this next series probably is something telescoping. So the hint is this denominator that can be broken up using partial fractions. So we have 3 over n times n plus 1 is a over n plus b over n plus 1. Now multiply by n times n plus 1. And that gives us 3 equals a times n plus 1 plus b times n. So inputting n equals 0, we find that a is equal to 3. And inputting n equal to -1, we find that b is equal to -3. So our sum can be written as a sum from n equals 1 to infinity, 3 over n minus 3 over n plus 1. And I'm going to factor that 3 out. So 3 times the sum from n equals 1 to infinity, 1 over n minus 1 over n plus 1. Now with telescoping series, you're going to need to give an expression for the nth partial sum. So Sn will equal 3 times 1 over 1 minus a half, plus a half minus a third, etc. The last term you have is 1 over n minus 1 over n plus 1. One prior is 1 over n minus 1 minus 1 over n. And you can see that everything cancels except for this one and this 1 over n minus 1. So Sn will equal 3 times 1 minus 1 over n plus 1. And so as n goes to infinity, Sn approaches 3. And so thus the overall series converges to 3. Determine the convergence or divergence of the following series. Well, not geometric since it's n cubed and not 3 to the n. So let's try the test for divergence. And let's see what happens. So find the limit as n goes to infinity of 3 to the n over n cubed. I'm going to use L'Hopital's rule, so I'm going to change my n's to x's. And I have an infinity over infinity limit. The derivative of 3 to the x is ln of 3 times 3 to the x, all over 3x squared. Still infinity over infinity, so do it again. So ln 3 times ln 3, 3 to the x over 6x. And one more time, still infinity over infinity, do it again. You can see we're going to have ln of 3, the quantity squared, cubed, times 3 to the x over 6. And that numerator goes to infinity, the denominator is 6. Infinity divided by 6 is still infinity. And thus, this series diverges by the test for divergence. Inverse tangent of n. Well, you think, how might I add that up? And if you can't figure it out, I would say try the test for divergence. So as n goes to infinity, limit as n goes to infinity of inverse tangent of n. So the picture of inverse tangent has asymptotes at negative pi halves and at positive pi halves. And as n goes to infinity, the value of inverse tan goes to pi halves, which is not 0. And so thus, this series diverges by the test for divergence. Now these last few examples are going to preview some things we're going to cover more in depth later on. So here I have something that looks a lot like a geometric series. So sum from n equals 1 to infinity. If I rewrite that as this, n equals 1 to infinity, x over 3 to the n, you can probably see that that is probably a geometric series and will converge for some values of x. So it's not indexed correctly, so let's do the re-indexing. Let's make it the sum from n equals 0 to infinity, x over 3 to the n plus 1, or the sum from n equals 0 to infinity, x over 3 times x over 3 to the n. Now this is a geometric series, and r is equal to x over 3. This will converge if the absolute value of r is less than 1, or specifically, the absolute value of x over 3 is less than 1. Now x over 3's absolute value being less than 1 means that x over 3 is bigger than negative 1, but less than positive 1, which means that x is in between negative 3 and 3. So those are the values that the series will converge for. And if your x is within those values, so if you have -3 less than x less than 3, this series converges to a over 1 minus r, which in this case specifically is x over 3, 1 minus x over 3, or x over 3 minus x. So for any x's within that domain, from -3 to 3, that series will converge to x over 3 minus x. If your x's are outside that domain, the series will diverge and you cannot use that last formula that we found. Here's another similar but a little bit more complicated one. So find the values of x for which the series will converge, and for these values write the sum as a function of x. So this one is indexed starting at 0, so no need to re-index here. It will converge if the absolute value of x minus 2 over 7 is less than 1. And that means that -1 is less than x minus 2 over 7, which is less than 1, or -7 is less than x minus 2, which is less than 7, or adding 2 everywhere, -5 is less than x, which is less than 9. So for x is between -5 and 9, you ensure that the value of x minus 2 over 7 is less than 1. And this will converge to a over 1 minus r, that's 5 over, not telling what a is, 5 over 1 minus x minus 2 over 7. If you're going to forget anything, you're going to forget that you need to have parentheses around that expression. And let's simplify that a bit by multiplying by 7, which gives us 35 over 7 minus, those parentheses don't drop yet. They do once you distribute and add 2. So this converges to 35 over 9 minus x. And our final example is a real-life example. So suppose you take a job that pays a salary of $50,000 for the first year, and during the next 30 years you receive a 5% raise each year. What is going to be your total compensation over the 30-year period? Okay, so year 0, the amount you get for year 0, your first year, is $50,000. The amount for your second year is 50,000 times 1.05. You get your salary plus that 5% raise, and whatever number that is, I don't care. A2 will be your salary from the previous year, given another 5% raise, so multiplying by 1.05 again. So that's 50,000 times 1.05 to the second. So note A0 corresponds to year 1, A1 corresponds to year 2, that's year 3. So year n, in this case year 30, will be the same thing as A sub 29, and that will be 50,000 times 1.05 to the 29th, and that would be how much you earn during the last year. Just so you get an idea of how much that is, 50,000 times 1.05 to the 29th. That last year your salary is over $200,000. So you've done well for yourself. Now notice that this is a geometric series, and we're technically summing from n equals 0 to 29, 50,000 times 1.05 to the n. Now if the upper bound was infinity, this geometric series would diverge, but we have a finite sum. Now when we proved the sum of a geometric series on the very, very first day, we had this partial sum, I equals 0 up to n, and that was a r to the I, and it equaled a 1 minus r to the n plus 1 over 1 minus r. And we use that to find the formula if the n was infinity. So this will allow us to find the sum from I equals 0 to 29, a r to the I. And plugging in the numbers that we have, it'd be I equals 0 to 29, 50,000 is my a, 1.05 is my r to the I power, and plug those numbers in, we'll have 50,000, 1 minus 1.05 to the power of n plus 1, so it's going to be power of 30, all over 1 minus 1.05. And when you plug that into a calculator, it's approximately equal to $3,321,000 $321,942. That's how much you will earn over a 30-year period, of course pre-tax and pre-expenses, but that's how much you've earned.